Welcome to the Microsoft Direct Compute Lecture Series. I'm your host, Robert Hess, and we're going to have a special episode now, a roundtable to help you understand exactly what Direct Compute is and how it might be applicable to certain tasks you're working on. Joining me in this special task is going to be this nice panel of experts we have joining us. First off, we have Justin Hensley, Senior MTS, AMD Office of the CTO. Then we have Eric Young, Manager of Developer Technologies at NVIDIA Corporation, and Chaz Boyd, PM Architect for Windows Graphics at Microsoft. Now, Chaz, this first question I want to take and direct to you is, what exactly is Direct Compute?
Well, Direct Compute is a new API that we shipped in Windows 7 that lets applications use the GPU for much broader applications than just graphics alone.
Now, I remember hearing with Windows Vista and Windows 7, we talked an awful lot about the GPU that's being used by Aero and stuff like that for doing some fancy graphics capabilities on top of Windows. Is that what you're talking about?
Well, it's part of the same trend. Just as the graphics of the Windows is using the GPU more, we're seeing interest in not just in non-graphics applications using the GPU more because they can find significant performance advantages.
So we're taking the graphical processing unit and not doing graphics on it.
Exactly. And
that first came out with Windows 7.
Yes.
So now, with Justin and Eric here from specific graphic companies where you're actually putting the GPUs on your cards, what do you think about Direct Compute?
Oh, we think Direct Compute is a great tool for developers because it allows them to leverage the GPU to do things. They can use it to do graphics, but they can also use it to do generic compute. So it's a great tool for developers to be able to write something once and have it run on a wide variety of systems. So we're very pleased with Direct Compute.
I think also Direct Compute allows you to do some things that you can do with graphics and compute now that were not possible previously. So there, as Justin mentioned, there are algorithms that you can write in Direct Compute that were not possible before. And then when you combine that with graphics, you have a very compelling API.
Now, when you say not possible before, I mean, I thought with a standard CPU, you could do anything on the computer.
Well, you could write it on the CPU, but that may not necessarily be the best experience for the user. I mean, there's some algorithms that are just not going to run as fast on the CPU, and they would be better suited to run on the GPU.
Why exactly? I mean, I'm thinking of a CPU, GPU, I throw instructions at it, and they process the instructions, and out comes a result. What exactly is the difference?
Well, in terms of raw compute horsepower, I think we found that through the evolution of GPUs, we find that GPUs have a lot more raw floating point horsepower, and they also have significantly large amounts of memory bandwidth. And those are two things that actually work very well for any data parallel or compute-intensive applications.
So it's like, since graphics are big bandwidth, and you got a ton of data, you're trying to go across the pipe onto the screen, and since graphics also, especially with more modern-day graphics games, stuff like that, you're needing to do the floating point processing, that is a different model than what the standard general-purpose CPU has been doing of just focusing on binary calculations, and that's kind of what you're saying then.
Exactly.
So how long has the GPU been used for doing processing in this fashion?
So people have actually been using graphics APIs to do compute for quite a while, but in general, you force the developer to jump through hoops to actually leverage the power in the GPU. So if you look, even with older DirectX APIs, people would use the API to actually do compute. So there's a famous example where people did FFTs using DirectX 9.
FFTs?
So it's fast Fourier transforms. In this case, what they were doing is they were using it to do ocean simulation. But you were using the graphics API, and it wasn't necessarily the best way to actually do the computation. So what Direct Compute lets you do is actually give you a more better access to the GPU so that you can do more interesting compute that you couldn't do before.
And in the past, you had also been doing it more, I guess, natively to the card, perhaps, rather than using an API that separated you from the actual physical hardware itself?
Right. So people would do the graphics APIs, and then one of the first GPU APIs offered by a vendor was a product called Close to the Metal by ATI. And in that product, you actually programmed an assembly language and you wrote command buffers. So it was actually a very low-level interface to the graphics processor. So there a very few number of people who actually sort of had the knowledge to actually do that. But so now that you have something like Direct Compute, it gives you a much more generic interface to the graphics processor.
I mean, plus the problem there too is that, let's say I was using an ATI card and developing this code for it, and one of my customers had an NVIDIA card. Either they're out of luck, or I've got to take and now rewrite that code for NVIDIA's hardware as well.
That's exactly right. So that's one of the great features of Direct Compute is that as a developer, you can write it and then have it run on multiple vendors of cards. So you're, as a developer, free from worrying about whether or not it will work on future generations of cards or even other vendors' cards.
Now, does that mean then that every single graphics card is the same as one another then?
No, definitely not. I mean, both vendors have strengths and weaknesses. Currently, our top-of-the-line GPU pushes around 2.7 teraflops. So if you look at so your question earlier about why people might be interested in doing compute on the GPU, you can see why the amount of floating point horsepower you have there. So there's one board that can basically give you almost 3 teraflops of computation, and I believe that's one of the sort of single most powerful GPUs you can get.
Mm-hmm. And Eric, what do you think about that? Focusing on using Direct Compute to access NVIDIA's strengths and power capabilities.
So definitely, I think what Direct Compute enables is it enables a new class of algorithms that were just not practical to use before. So you can think of algorithms like doing optical flow. So optical flow is a fundamental algorithm that is used for things like tracking pixels on the screen. So anything like if you were to remove video shaking from a video, it would basically be something that you can do on the GPU that wasn't possible to do interactively before.
Now, I understand we've actually got a demonstration of that, of someone actually using this to show a handheld camera, I guess it is, and then doing post-processing on that to see what it looks like. Let's take a look at that video. So we have here in this video this scene of a car, and then on the left-hand side, we're actually seeing the raw video that someone took, and the right-hand side where it looks a lot smoother. Now, this is simply post-processed. It's not the camera itself, a different camera that's managed. It's the exact same footage. It's just being post-processed through Direct Compute to remove the shake.
Yes.
How is that done exactly?
Well, the Direct Compute API is used to evaluate the positions of all of the different parts of the frame, the objects that are in the scene, for example, or just background, and then it looks at that across multiple frames to see where things are moving. And then from that, it's able to figure out how the camera should be shifted in a way to compensate for any shake that's introduced by the person, in this case, walking down the street.
So in other words, we have things that aren't supposed to be moving, like trees aren't supposed to be moving, and signs aren't supposed to be moving, but then we have these cars that are moving, and it's able to differentiate which is the supposedly steady things, which are the moving things, and it's actually shifting and rotating the graphic in each frame
Yes.
to make up for that?
Exactly.
And is that happening in real time?
Yes.
Wow, that is pretty amazing. Now, to me, we're doing graphic stuff there, but a couple times we've mentioned that it's not even for necessarily graphical stuff you can use this for. So if I'm using the GPU through Direct Compute to do stuff that's non-graphical, what exactly does that mean?
Well, we've seen cases where algorithms that used to be, for example, considered part of physics have been implemented using Direct Compute. So the way a piece of cloth behaves when it's moving in the wind, or possibly fluids in a container sloshing around. It's a very complicated simulation that would take a long time if you didn't have a high-powered system to implement it on.
So you focus on basically doing calculations for fluid dynamics.
Exactly.
Using the GPU. And Direct Compute, by its name, Direct Compute, I'm assuming then it has some callback into DirectX and the capabilities that normally we consider for gaming?
Yes, that's one of the key features, is that because it's part of DirectX, it integrates very closely with Direct3D, so that whatever you've just computed, you can now display in 3D immediately after. So a lot of these scenarios that we work in, the user wants to see the answer within a 60th of a second. So having them tightly coupled like that enables those scenarios to be very efficient.
So instant gratification, in other words.
Exactly.
People moving further and further away from the old punch card decks. They have to stand in line in the batch processing room. And boy, when I was a kid, well, we won't even go in there, but So how long has Direct Compute been around then?
Well, we shipped the final release with Windows 7 last fall. There were betas that were available about a year before that, over that kind of time frame. And there continue to be updates via the DirectX SDK process over time with new samples and examples of how to use the API.
Mm-hmm. And NVIDIA and ATI, you guys have both been actually working with Direct Compute throughout this whole process?
That's correct. So in this past fall, when we launched our most recent version of cards, the HT5000 series of cards, at our launch in the fall, we actually had 2 Direct Compute enabled demos. Both those demos were actually very graphics focused, but so they used Direct3D in combination with Direct Compute. So we would do some part of our rendering in Direct3D and then do some computation in Direct Compute, but then ultimately we'd want to be able to see it. So we've been very active in enabling Direct Compute. And then one of the things we've been doing lately is actually looking at things like cloth simulation for games. So how you can enable something like bullet cloth to actually be accelerated in Direct Compute, and then that could be used in games as well.
But you're saying that you've actually got to support Direct Compute in your firmware and hardware. It's not just Windows doing something unbeknownst to you. You've actually got to do some work to focus on making sure that Direct Compute works on your cards?
Oh yes, there's definitely a level of support and development we have to do. So there is a Direct Compute driver that is actually included with our drivers that we release on the web, and basically we have to go through Wiggle, and we also have a lot of internal QA tests that we
go through Wiggle?
The Windows Hardware Qualification Lab. So Microsoft has a set of tests that basically are designed to validate a driver. And part of that certification process has to go through Wiggle, and then internally NVIDIA has a set of application and tests that we develop in-house to also qualify our driver.
Now, does that mean that me as a customer, I need to be concerned about what video card I'm getting with my machine to make sure it actually works with Direct Compute, or for the most part, are most video cards now supported? I guess, Chaz, that's probably a question for you.
Well, one of the purposes of this certification suite is to guarantee the performance capabilities of Direct Compute are consistent between these vendors as defined. And both of these guys, we're very grateful. Both companies made changes to their silicon and to their drivers to specifically target the Direct Compute API.
So if I'm using an old machine that I used to run Windows 3.1 on, chances are that graphics card probably doesn't support Direct Compute?
Yes, that's
probably the least of my troubles, though, isn't it?
Yes, you need a DX11 or a fairly recent DX10 card.
So it sounds then what we're saying is that Direct Compute basically is a specialized API that gives programmers access to a different level of power that's available through the GPU than what they might have had available on the CPU.
Exactly.
So hopefully that gave you an idea of what Direct Compute is. What I'd like to investigate now is exactly what sort of applications are possible using Direct Compute. So what applications are we seeing people do using Direct Compute?
Well, some of the applications that we've done in the past when we first launched our cards were very graphics specialized, but one of them was a particular technique that's very hard to do in graphics called ordered independent transparency. So one of the demos we do is we leverage Direct Compute and Direct3D to do this classic problem in computer graphics that you can't easily do with a standard graphics API. And then another example would be...
Which would be kind of more, I'm thinking like a game type application.
That would be a game type application, but there are actually applications in volume rendering which would have more scientific visualization type applications. One of the other applications that we had was what's called depth of field, and that's trying to simulate how a camera basically warps an image and distorts an image depending on what the size of the aperture is. So again, that was more geared towards games, but you can think of it in lots of video applications as well.
But you were still talking graphics. I mean, partially I have a hard time getting past the concept that I've got a graphics card on my computer and I've got a specialized API for accessing it. Why am I doing something that's non-graphical on that graphical processing unit?
Well, as we talked about earlier, just some of the performance that's available in a graphics card, if you look at an application that's tailored for running on the GPU, it can easily run 10 to 100 times faster than what would run on a CPU, just because of how much floating point horsepower is in there. But again, what you really want are data parallel applications. So it turns out if you have a data parallel application, it runs quite well on the GPU.
And why does parallelism come through better on the GPU than it does on the CPU?
So a lot of that comes from the structure of the GPU, so how the GPU is actually built. So Modern GPUs have what's called a SIMD, or single instruction multiple data model. And so they operate one instruction across multiple pieces of data, and they operate in these very parallel fashion. So when they do this operation, that maps very well to data parallel type applications. Whereas if you're doing something that's purely sequential, that's not going to map well to the GPU, just because of how we leverage all the floating point units on a GPU is in a very parallel fashion.
So even though graphics are one of the sorts of things that requires an awful lot of computational power and other stuff like that, if I'm doing an application that still needs number crunching, I could take and be getting benefit out of direct compute and using the GPU instead of the CPU.
That's correct. So some other examples that we mentioned earlier were the fast Fourier transform, which has lots of uses in image processing. So one example that we can talk about is image denoising. So I believe we have an example of that we can show.
Oh, let's take a look at that. So now we're looking at this demo. Chaz, can you explain to us exactly what we're seeing here?
Well, on the left side of the image, we've got a sample of some data that's simulating something that was potentially acquired from a satellite, but has got a noise pattern that's contaminating the signal. And it turns out that if we take that image and convert it to the frequency domain using the FFT to create the central image, the noise pattern that was spread out over the entire image is now localized into a small number of points.
And again, FFT here was fast Fourier transform.
Exactly.
And so that center image is the globe still, even though it looks like a bunch of static to me with a couple bright dots in it. It really is the globe. It's just being looked at in a different manner.
Right. In fact, we can now take a little paint program or some other process and erase those points. And then when we convert that back, using the FFT again to convert from the frequency domain to the spatial domain, we end up with an image that is free of the artifacts on the right.
So I mean, it could be that people in the audience aren't quite able to see exactly what's happening here because they might be watching this video through a small little screen and not a big gigantic display on their wall. The globe on the left-hand side has some visual artifacts in there that are undesirable. And the globe on the right, through the cleanup process that you do with the fast Fourier transform and erase those little teeny bright spots, actually removes, for the most part, all of those little specks. And I'm sure if you did a better job at erasing those little globe marks, we'd have a far better image there on the right-hand side.
Yep, this is exactly the type of technique that JPL and other similar companies use for this type of operation.
Now, to make this easier to see, what we'll do is we'll put this video on the web so you can download it, look at it full screen or something like that, so you get a better idea of what's happening. And what I'll do in wherever you're watching this video at, we'll have a link to where you can actually download that video. Now, even though we're still showing graphical stuff here, like the globe and stuff like that, I'm assuming that the same sort of capabilities using a fast Fourier transform with data can be used for moving artifacts from almost any data, like let's say it was music or something like that rather than a picture. Would it still work for that on the GPU using direct compute?
Yep, that's exactly the sort of thing that the frequency space is really good for. We have libraries in DirectX that help you convert 1D and 2D signals like images. 1D would be audio.
Now, so we've kind of gotten to the point where we can hopefully understand that direct compute is for more than just graphical games and stuff like that, and also used for people that are doing very deep calculations, whether it's NASA or Boeing doing noise tests and stuff like that. If someone in our audience is not working for someone doing high scientific calculations, is there still some value they can get out of using direct compute?
Well, we've seen areas where people have been using GPUs and techniques like direct compute for financial simulations, which you can test out a whole bunch of scenarios if you've got 1,000 processors to use in that test. So that's one of the fields that people are actually getting use of these products today.
So the main aspect then is just if you're really needing some high-powered computations done, so that'd be finance, that'd be music, that'd be graphics, that would be calculations, all that sort of stuff. You can actually use direct compute from that standpoint. I mean, it sounds like we're still talking about a slightly specialized audience and not your just general developer. I mean, let's say I work for a company like Intuit or something like that, doing a check balancing application. Is there a value I might have about using direct compute for doing some of my processing with?
Well, there are certain applications that it's not a good fit for. If you're just doing a fairly small amount of calculation, like some individual's taxes or not a country's taxes, then it's probably not the ideal approach to use the GPU for that kind of problem. Things that involve collecting a large number of different places in memory and computing on those is really the best sort of problem for the CPU to do.
So maybe the same sort of stuff that, like Microsoft also has this HPC effort going on for high-powered computing. The same thing, if I'm thinking about, gee, I'm needing more than just this dorky little computer sitting on my desk can get at me, maybe it's time to look at the GPU and see if it can provide that extra horsepower that I may be wanting for that application.
Exactly. It's like your own personal cluster.
Yeah, there you go. That's one way to think of it. A little supercomputer right there in that graphics card. So did you guys ever think that a graphics card may be able to be used in this fashion?
So I personally have been doing sort of what's classically called GPGPU for around 10 years now. So through school, we were doing sort of the old style applications where we actually had
Straight to the metal.
Well, it was even prior to that. So it was basically abusing the graphics API to do what you want. But then you had a very limited world that you programmed in. So it's great to see an API such as Direct Compute, which allows you to actually express much more complicated algorithms than that were possible before.
So if you want to look at like programming GPGPU before we had Direct Compute, imagine that you had DirectX 9 capable hardware, and while you could do GPGPU computation on it, you're actually very constrained because of the way of memory addressing on such cards. So what you can typically have is support for scatter reads from memory, but you cannot do scatter writes. So basically you're constrained to, for every pixel that is being written, you can only write a single address.
Yeah, it was very painful. It was like computing, except that you could write to any data structure you want as long as it was an array, a 2D array. That was it. Couldn't
Nice.
write to a linked list, couldn't write to a tree.
Oh, no linked list on computers. That's kind of limiting, I would think. Yeah, but now with Direct Compute, it actually enables that, so I can actually access more of the power directly that I want to.
Yep. This OIT example uses a very complex data structure to store intermediate results.
So do you think we'll actually see new styles of application come about because of this capability of Direct Compute, or is it simply making existing applications easier and faster to write?
Well, at first we always see people who just take their existing algorithm and optimize it, and we're seeing advantages coming up in several applications already. But then over time, I think it'll be in the next year or two, we'll start to see people who actually push the limits and do things that we didn't expect.
Now, is Windows itself making use of Direct Compute?
Well, there are a lot of components inside Microsoft that are starting to adopt the GPU computing model like Direct Compute. And Windows itself, well, there's always lots of work going on inside Windows, and we'll just have to see what happens in a future release.
So it sounds like we're saying then is that application developers who feel like they're pushing at the limits of what a standard desktop or laptop computer can do, they might be able to take and find better advantage taken by using Direct Compute, so they can access the GPU and the capabilities specified there.
Exactly.
So hopefully now you have an understanding of what Direct Compute is and the types of applications that can be developed using Direct Compute. And maybe, just maybe, you're saying, hey, that's the type of applications I'm needing to work on. The next question you might have is, how do I do it? So let's cover that. How do you write a Direct Compute application? What's the starting point?
Well, I'd suggest starting with the DirectX SDK. There are a variety of sample applications in there that are a very good way to learn the initial Direct Compute API. And then there are similar SDKs with similar types of samples that are produced by our hardware partners as well.
So the whole aspect is starting with a good formal understanding of what the code looks like. And so samples have always been a very good way of understanding what applications are capable of doing, just modifying those samples until they do stuff. So do you have any specific samples you guys feel are a good starting point for different type of applications?
So for the very first beginning examples, the examples distributed with the DirectX SDK are quite good just for getting your feet wet with the examples. If you want to go to more advanced examples, both our companies have examples where we provide applications that you might be interested in A lot of the ones that I'm personally more involved with are much more graphics focused, just because that's, in general, after you get done with the computation, you like to see it. So we tend to do things that are much more graphics focused.
Graphics are fun anyway. It's
Yeah.
like, just like playing a game, hey. But I mean, let's say I'm wanting to do a fast Fourier transform application, like we saw in that one demonstration. Is that an example application we can start with, or is there something similar like that I can do things with?
Yeah, there are applications that are very similar to that, that show how to just do the basic, start it up, initialize, get the data in, get the data out, shut down. Those steps are clearly delineated in the basic samples.
Mm-hmm. Now, what about from a programming background? So I'm a programmer out there, and I've had some training in a couple different languages, and I've got existing applications I'm doing. Where might I need to go from a training and understanding standpoint to understand the language to use, the actual tools themselves? Like, what compilers does it work with? Does it work with Visual Studio? Does it work with my .NET application? What are some of the considerations I need to make to take my existing application and allow it to use Direct Compute?
Well, it works right now with the Visual Studio compiler set. We do have interfaces that allow you to work the API through managed code, but it's really sort of a different programming model from C# or any of the other managed languages.
So I'm needing to focus on writing an unmanaged component that is doing some of this, which quite frankly, if I'm doing high-end calculations, I'm probably doing that unmanaged code already, because .NET isn't specifically designed to be that computational engine. It's meant to be something exactly, more write the application in bulk itself.
Yeah, that way you get the ease of developing and customizing your user interface using managed code, and then you still get the performance of the core algorithm being implemented on the GPU.
Mm-hmm. So what tools do you guys use for developing your apps with?
So NVIDIA also has a GPU computing SDK that basically includes Direct Compute, CUDA-C, and OpenCL samples. For the SDK, we have quite a few samples that just illustrate different types of algorithms that are used, and a lot of the focus that NVIDIA has been moving forward is for high performance computing. That said, so we have this tool that NVIDIA is developed internally. We call it Parallel Insight. So basically, Parallel Insight is a tool that allows you to debug code that's running on the GPU, as well as perform performance analysis from a system level point of view. So the first version of Parallel Insight, we supported debugging on the GPU, so we could debug CUDA-C programs, DirectX shaders, and now we are working. It's a higher priority for NVIDIA to support Direct Compute. So I would expect that with the Direct Compute capability debugging on the GPU, I think that's going to be a very compelling reason for developers to want to use and develop for the GPU. Also, Parallel Insight offers the ability to profile on the system level. So if you think about it, well, I might want to profile what's running on the GPU, but what about what's running on the CPU? So maybe there's a CPU thread that is blocking my kernel that I'm running on the GPU. So how do I get that information? And that's something that Parallel Insight offers. It gives you an entire system level overview of what's running on the entire system, what's running on the CPU, what's running on the GPU. Am I getting overlap am I running the CPU code, and am I running GPU functions at the same time? That's something that's important that developers need to know, and I think that's something that they'll find value in having such a tool.
I suppose that's a good point, because it's not just simply having printed out lines of code, and some of that code is tossing stuff to the GPU and some of the CPU, but actually making sure that the tools you're using understand who's running what code and be able to see that processing. In the same way, even just a parallelism application, understanding which CPU is running a particular amount of code is a very big issue from that standpoint. But in the same issue with the parallelism, I'm needing to, from an architectural standpoint, think about my application slightly differently. It's not just lines of code and just some of just happens to be here and some happens to be here. I have got to intentionally be segmenting my application up to make sure what's running. How does Direct Compute focus on that aspect?
Well, one of the key elements of that problem is getting the data to be in the right place at the right time. If you've got some data that you want to process with the CPU for a while and then process with the GPU, you have to transfer it across in time so that nobody has to wait for that data to be there. And we have these resource objects that you'll learn about in the later lectures that encapsulate that data and make it clear to the programmer when exactly the data is at which end of the pipeline.
So to talk more down to the bare metal programming, back in the old days of assembly language, I've got a register that's on the CPU and a register that's on the GPU, and I needed to make sure that the variables that are actually mapping to the registers are properly defined, and I'm then moving it across, and then the application itself is doing the data transfer.
Yeah, it's more like not so much registers, but just arrays of data. Typically a megabyte, even gigabyte array will be processed in the custom video memory that the graphics chip has its high bandwidth interface to.
And I'm assuming that can even take a while. And so if I'm constantly
Right.
moving back and forth, I want to actually get the stuff in the CPU all taken care of first, and then
Right.
move it all in mass over to the GPU and
Yeah.
process it there, and not be bouncing back and forth all the
Right.
time. So does it take an awful lot of re-architecting your application to make it work in this model? If I'm currently got it running properly on the CPU, just not as fast as I'm wanting it to, is it a big job to move it across to use direct compute?
Well, I think as long as you're aware of some of these issues, it's fairly reasonable. The thing you want to do is avoid, say, having the GPU talk to video memory and vice versa, if you can, and just minimize the amount of data that you have to copy over. The GPU is a lot faster than the CPU, but the interface to get the memory to it is somewhat slower than the CPU normally has. And so if you spend a lot of time copying data across that, you can kind of eliminate the advantage of using the GPU.
So, I mean, programmers that need learning and training aspects, I mean, are there avenues open for them to get their training?
Well, we have got a set of tutorials that cover the basics introduction, and those are included in the same DirectX SDK. And then, of course, the rest of this video series will have explanations of how to go through a lot of these algorithms using direct compute.
Mm-hmm. But I think a lot of developers out there in the audience watching this, I mean, their next step is going to focus on, where do I go for information? So the SDK is a really good spot for that. Are there any books out there yet, or is it still too soon for direct compute books to be available?
I'm not aware of any that have shipped yet.
So that's a good opportunity then for some people watching the show. If they spend some time with direct compute, maybe they can make some money on the side writing a good application book for it.
Yep.
Yeah. And maybe you guys should write one of these books. You got a book in the works yet?
We have lots of projects in the works. So
Now, when you guys are helping developers today, what are some of the big problems you see them running into in developing applications using direct compute?
So one of the typical problems Chaz mentioned earlier, which is you don't want to basically move data back and forth needlessly. So typically what you'd like to be able to do is move the data to the GPU once, do lots of processing, and then move it back. And so as Eric mentioned earlier, NVIDIA has a tool. We have a similar tool called GPU Perf Studio, which will give you the ability to look at performance counters on the GPU, but also look at how much time is spent moving data to and from the GPU, and give you the ability to figure out what part of your application is actually limiting your performance.
And I suppose if you're at the stage where you're feeling a little hamstrung by just the CPU already, you're going to be used to paying attention to some of those performance numbers and understanding exactly how to take and investigate your application to find out where those roadblocks are. And so these tools are going to be, flow pretty well into the work style that you're already going to be having for doing that sort of stuff with.
That's correct. And one of the other parts of these tools is that for people wanting to do sort of last mile optimizations, which if you're doing very high performance computing, you're used to trying to get every little bit of performance out of the machine as possible. So we have tools that allow you to go down to the very low level assembly. So you can try to you can once you understand the GPU well, you can actually figure out what part of your kernel is actually limiting your performance and figure out ways to actually optimize it even further. But those are in general for people looking for sort of very last mile optimizations who are doing, want to get that last 1% out of the machine.
Mm-hmm. Now, are all these tools part of the DirectX SDK, or are these separate offerings that different companies are providing specifically for their cards?
So GPU Perf Studio is an AMD specific application that it looks at the performance counters and allows you to look at optimizing and debugging direct compute and DirectX applications specifically for our hardware.
Mm-hmm. And the same thing with NVIDIA, you've got a separate set of SDK tools?
Yeah, so we have a set of tools, Parallel Insight, which are designed specifically for running on NVIDIA GPUs. I mean, we also have performance counters and also advanced features to basically support like single-step debugging, examining contents of video memory, examining contents of registers. So all of those things are are unique to NVIDIA hardware, and those are exposed through our tools. We also have, at least for developers that are just getting started, we have lots of good resources. We put them out as like best practices guides for programming on the GPU. I mean, independent of which language you choose, I think the best practices guide applies to whichever compute language you prefer. And I think we have a set of guidelines that we provided based on experience we have learned from working with developers. What are their pain points? What are the things they should be focusing on, and in order to determine how to best optimize their application.
What do you think some of the off the top of your head key points are to remember if you're optimizing your application and developing it for direct compute?
So I think probably the majority of the performance is going to be with efficient memory accesses. So within our GPU architecture, basically GPUs, when they read and write memory, they read them in bigger chunks. So if you can ensure that you follow we call it memory coalescing rules, then you basically will get efficient access to memory. So the minute you no longer satisfy these memory coalescing rules, then basically the GPU has to issue more memory requests, which is less efficient. So generally we find that if you can follow these guidelines, you'll basically be able to achieve close to the theoretical bandwidth available on the GPU. And then there's other levels of optimizations that we also offer, like we have instruction level optimizations. We have guides about how to effectively use the shared memory between multiprocessors, as well as guidelines for how to basically eliminate divergence. Divergence meaning like if you have threads within a warp running on different conditions. So all of these guidelines, I mean, we basically provide a very good best practices guide. It's like a document that we have on the NVIDIA website, and I think developers find it extremely useful.
Mm-hmm. So it sounds like at the top level we have the DirectX SDK to give you a nice global look at what direct compute is, and then the different manufacturers themselves have additional tools that are somewhat specific to their own hardware to assist you further. Mm-hmm. And that's no different than if I've got a Dell computer, an HP computer, there's going to be certain things that allow me a better access to understanding how those systems work. Because we're basically just talking about different vendors that all operate underneath one big umbrella, which is the direct compute. And you've got some tools and capabilities and best practices to help me develop applications better. Do we see some of the tools moving forward as taking better advantage of direct compute? Do we see this becoming part of the global mindset of an application developer in the future, or do we see this as being still a kind of a slightly niche market in the same way that DirectX is kind of like a niche market for developers?
Well, our goal certainly over the longer term is to have direct compute treated just like any other language. And, it's just a question of how long it's going to take us to even out the sort of capabilities that you have on the CPU versus the GPU. We're trying to make things as consistent as possible. That way you can transition as many skills as you have over to the other side with the minimal amount of having to relearn things. Now, some stuff you do have to relearn, but other things, it's just sort of historical difference. And so we'd like to eliminate a lot of those historical differences.
Mm-hmm. I mean, obviously, any new technology that comes down the pipe is going to take a little bit of learning to understand how to use it properly. But obviously, we want to make it as easy as possible for people to use our software, our platform, or our hardware capabilities that we're providing to them. Because, hey, we're writing this stuff for a reason. We're adding great capabilities to it. And so people make use of our hardware. If our hardware's got a faster GPU on it, and it's just sitting there not doing anything, people are wasting their money buying that hardware. They should get some money out of it by doing some cool graphics capabilities or even financial computations or whatever else on it. So, I mean, it sounds like what we have then is an application model that allows developers to choose where in their application they want to take and make use of the direct compute capabilities. And as long as they do the right best practices capabilities, using the tools properly, they can take advantage, make sure their applications run as fast as possible, and hopefully achieve what they're needing to do on the existing hardware that they're already using. This morning when you woke up, you might not have known exactly what direct compute was, but hopefully now you've got a little bit better understanding of what direct compute is and how it might be able to assist you in your processing. Now, in a show like this, we can't cover all of the details associated with direct compute, and that's why we have the Direct Compute lecture series. a series of episodes that's going to carry more and more details about how to use direct compute in your applications and how to take and focus on writing applications. Fortunately, some of us has actually had some experience with some of these lecture series episodes. Chaz, I realize you've got an episode that you've been in. What sort of things you're going to be covering?
Well, the very first talk is just a high-level overview of some of the things we talked about today, with a little more detail about, where exactly is the CPU within the machine, where is the GPU, what are the similarities, what are the differences, how you decide what parts of your application you want to put on which type of core. And then after that, there's another lecture as well by Matt Sandy, who covers the fundamentals of how you communicate to memory through the direct compute model, the different types of memory resources that you can operate on using direct compute.
So in other words, we're going to kind of do a high-level introduction of what direct compute is. In these episodes, they're going to actually dive in deeper, showing code, I'm assuming?
Yes, the further you go, the deeper it gets.
Oh, there you go. That's where the important stuff's at. Now, so Eric, I guess your company is also involved in doing some of these episodes. What sort of things you can be focusing on there?
Yeah, so my colleague James Fung, he's going to be presenting two series. One is on GPU optimization. So some of the references I made to best practices, he's going to actually go through a simple algorithm and basically walk through, how can you optimize this to run well and use the maximum available compute power and the memory bandwidth available on the GPU. And he will also be going over another series about graphics and interop. So we have several direct compute samples that actually show how can you have direct compute samples that, let's say, perform some kind of simulation, and then how would you use that information for rendering in the graphics. So we have examples of image processing using like a compute shader for doing like a rolling box filter. We have an example of how you can do particle simulation using direct compute and visualize it on the screen. And then we also go through a code walkthrough of a FFT ocean simulation. So basically we use FFT to create a more realistic ocean simulation. And it basically gives you a new level of realism because we're using compute for doing the simulation.
So it sounds then, Eric, that NVIDIA is going to be focusing pretty well on making sure that developers understand some of the optimization techniques that are possibly using direct compute.
Yes, that's correct. And we're committed to supporting developers through our developer website. We have various guides and best practices that we publish for developers, and those are definitely available and freely downloadable on our website.
Okay, thanks. And Justin, what do you think your company's going to be doing for the lecture series?
So one of my colleagues, Lee Howes, will be talking about some work he's been doing on class simulation. In particular, what we've done is we've taken the open source physics engine called Bullet, and we're adding class simulation to it that's accelerated in direct compute. So Lee will go through talking about optimizations that you have to do when you take a solver that's meant to do class simulation on the CPU, and some of the tricks that they use on the CPU don't necessarily work well on the GPU. So he talks about how you can directly take the solver over to the GPU, but if you want to actually leverage the GPU more with direct compute, how you can change that solver to make that class simulation even faster.
I don't know, for some reason, thinking about bullets and class simulations, I can't help thinking about the Matrix for some reason. But maybe that's just me. I mean, but it sounds like overall, we've got a good set of lectures coming up to help people really understand the capabilities that direct compute can provide them and get a little more detail than we've been able to get here on stage with showing some real code capabilities and pointing people to actual applications that can assist them in that. So hopefully that gave you a good introduction to what you need to know about direct compute and how it might help you in the applications you're developing. Please make sure you stay tuned and watch further episodes of the Direct Compute Lecture Series, and all your questions I'm sure will be answered. Well, most of them anyway.